Now, we have, at this point in time, a discussion of hemoglobin. Now, if you've got questions during this, don't hesitate. Please ask them. I will do my best to answer them. And I'm sorry for scaring anyone. Um, what's exciting about today is we are going to talk about a bunch of different stuff, and this is going to bring back some Gen Chem 2 stuff. Milo, that's a great question. And you will see your exam grades by the end of today. I haven't had a chance to record my video where I go through the um, questions, and I don't want to release the exam grades until, I do that, and then I can kind of do my analysis of like, okay, full transparency. I can look at the distribution of the question or of the answers. And if there are questions that are like 96% of the class got this incorrect, and not necessarily 96, but a high percentage, that's one where I'm going to look at and be like, Joel, was that a good question? By the looks of it, it was either not a good question or there was something fundamentally wrong with how you approached it in your instruction. So I'm going to do that so that I can either award credit to all those sorts of questions or remove them. And just so everyone's on the same page, whenever I do encounter that, I don't remove a question, but rather I award credit to everyone because if I were to remove a question, that would shift the weight of every other question, giving it a higher value, and I don't want to do that. Um, in addition to that, um, your exam had 33 questions and they were 3 points apiece. So I have to add back 1 point to everyone's question or everyone's grade. So it's graded out of 100 as opposed to 99. Now, with that, I'm going to have all that done by the end of the day. You'll get an announcement on Canvas about that, and we'll proceed from there. Now, one last thing that I got to do. Done. Um, okay, so we've got a little bit of stuff that's not necessarily review, but we've talked about it a little bit already with respect to hemoglobin. But what we're going to get into today that's really much more important and significant with respect to hemoglobin is we're getting into these what are known as oxygen binding curves. Now, oxygen binding curves, what the oxygen binding curves are basically how we, preview there, how we evaluate different hemoglobin proteins. And not just hemoglobin proteins, but like myoglobin and any other protein. But with that in mind, let's tackle our first question. How many O2 can hemoglobin bind? I think I've got the timer for 60 seconds, but I'm pretty confident everyone's going to knock this one out pretty quick. And I'm comfortable saying that we're going to get 100% correct on this one. In the event that we don't, that means somebody might just be like, "Ah." If you're that person, don't do it. Don't ruin my numbers. They're not my numbers, but okay, there we are. 1 minute. Sure. If it is 100% correct, I'm going to give everyone in the class 1 bonus point on their most recent exam. Okay. This is a tense moment. No! Okay. Hemoglobin can bind four proteins. Hemoglobin can bind four oxygens. When it is completely saturated, it gets four oxygens. Myoglobin can bind one. I don't know what can bind two. It's not hemoglobin or myoglobin. I think next class period, we're going to have another question where we're putting it all on the line. You're absolutely right, Morgan. It's got four prosthetic groups. Each one of those can bind one. HB is not only the Marvel comic and Ron Perlman movie Hellboy, but HB, in this case, we're talking about hemoglobin. I'm going to go ahead and assume that the people who marked A and B were probably mistaken and they were thinking about the comic book Hellboy. But that doesn't reverse my decision. We're going to have another question at the beginning of the next class period where we're going to put it all on the line. And if we get 100% correct, it's one bonus point. Now, with that said, no collusion. No, hey, this is what it is. Okay, now here we go. So this is a little bit of a refresher. Protein ligand binding. I mentioned this last time, or I mentioned this before our last test, that hemoglobin binding to oxygen and myoglobin binding to oxygen, those are just models. It's a great model because everyone cares about hemoglobin, but also it's a simple model and it kind of illustrates the differences between proteins that bind one substrate or one ligand, and then proteins that can bind multiple, and the implications of that. And with respect to that, allostery, which we talked about allostery before the last exam, but we're going to get deeper into it this time. Now, the functions of many proteins involves reversible binding of other molecules. That other molecule is a ligand. A ligand itself can be a number of different things. A ligand can be a small protein. It can be a small organic compound or an inorganic compound. And of course, this small, we're talking about something that is on the order of like 10 kilodaltons. So that would be approximately 10,000 grams per mole. So that's our measure of small or large. Larger than that would be considered a large molecule. So that's not a hard and fast number, but we're talking about something that, ATP is a great example of a small molecule. Now, ligand binding is importantly non-catalytic. It often causes a protein to undergo a conformational or a shape change, and it can be regulatory. Okay. We've got two different types of blood that are important for hemoglobin binding to oxygen, and they are arterial blood and venous blood. So blood that's found in our veins is going to be our deoxygenated, and blood that's found in our arteries is going to be our oxygenated. Now, with that in mind, this illustration, like lots of illustrations, they kind of take out the complexity of it. They kind of simplify it. And that's intentional. That's to, hey, I want to communicate this idea. One thing that's shown here is we've got hemoglobin here that is completely devoid of oxygen. So that means this hemoglobin is effectively like this, as opposed to HbO2, and then this would be in parentheses 4. This completely deoxygenated hemoglobin isn't really realistic. Instead, what typically happens with hemoglobin, and again, we'll get deeper into the details and the nitty-gritty of this later, is hemoglobin loads up 4 oxygens, and then it goes to the tissues and drops off like 2 or 3 of them. It's not going to drop off all 4 oxygens. Now, with that said, that's some of the nuance and complexity of hemoglobin as an oxygen binding protein, and an oxygen binding protein that binds 4 different, or 4 identical, but 4 unique O2 molecules. Now, myoglobin and hemoglobin, they are very similar to one another. Structurally, they look the same, but there are some differences. Hemoglobin, tetramer. If it has 1 to 2 oxygens, will it inhibit its ability to transport CO2 out? No, it will not. And so that's a great question, Andrew. So it's if hemoglobin has gone to the tissues and drops off 2 O2s, for example, well, then it's got 2 left. Where it's going to bind CO2 is different from where it's going to bind O2, or it has an additional place that it can bind CO2. So it's almost like I always think of hemoglobin as like a dump truck. It puts four O2 molecules, takes it to the dump site, dumps off two of them. Then CO2 doesn't necessarily get in the back of the dump truck, but instead gets in the cab of the truck. So it finds another place that, hey, now we can leave. We've still got those oxygens back there. It's not fully deoxygenated, but we're taking CO2 with us. I hope that analogy makes sense, and I hope that, you'll stay tuned for when we talk about where CO2 is going to bind. Now, with that said, here's our structures that are similar, but with a little bit of a difference. We've got our myoglobin monomer and our hemoglobin tetramer. An important thing to remember about them is that myoglobin is not, or hemoglobin is not four myoglobin subunits. It's not like, oh, well, now we've reached a critical mass or a critical concentration of myoglobin. We can make hemoglobin. These are distinct proteins. Hemoglobin, we'll talk about the structure a little bit on Friday and or Monday. Hemoglobin is four different subunits. As we previously talked about, we've got the beta 2 subunit, alpha 2, alpha 1, and then hidden behind this HB tetramer is our alpha 2, or sorry, our beta 1 demarcation there. So it's four subunits that assemble that are different from myoglobin. Now, this depiction right here. Okay, so if we look at this graph on the right-hand side, we've got relative absorbance on the y-axis and then wavelength on the x-axis. This shows you the light that is absorbed in the visible light spectrum by different forms of hemoglobin. We've got oxygenated hemoglobin and deoxygenated hemoglobin. What I want you to recognize is that deoxygenated hemoglobin, it has a lambda max of approximately 560 nanometers. So that blue peak right there denotes where deoxygenated hemoglobin is going to absorb the most light. Now, I believe that this would be your completely deoxygenated hemoglobin. So this would be like somebody has purified hemoglobin given an oxygen-deprived environment and checked the wavelength that it absorbs. Now, this is kind of unique because not every protein is going to bind light within a visible light spectrum. So not every protein has a color to it. So detecting proteins can kind of be challenging. Now, with that said, our oxyhemoglobin has two major peaks at 580 nanometers and at 540 nanometers. Okay, the significance of this is, and this is all related to the binding of O2 to that Fe2 plus, that divalent iron heme complex, alters the electronic state of that complex, which results in that color change. Excuse me. Now, this is where we have our dark purple, our venous blood hemoglobin, and our scarlet, our arterial blood hemoglobin. Now, I think that when it comes to, I just said that the deoxygenated hemoglobin would be the purified. I think that you're going to have some of these absorbances vary a little bit whenever you have that partially deoxygenated hemoglobin. Now, with that said, I would like to ask anyone if they know where the bluegrass state is or what the bluegrass state is. This is a little bit of a detour, but this is just the interdisciplinary aspect of biochemistry. What is the bluegrass state? I'll give you a hint. Mitch McConnell. I'll give you another hint. Kentucky! Absolutely right. If you've ever been to Kentucky, it's an absolutely beautiful state. It's an absolutely beautiful place. They've got a Corvette museum in Bowling Green. But one other thing that they have in Kentucky is a population of people that for a very long time lived I guess I could say a very isolated life. There, I don't think that this is necessarily I think that this is somewhat derogatory, but a population of people known as the Blue People of Kentucky. They were a family who exhibited a rare genetic condition known as methylmyoglobinemia. This was characterized by abnormally high levels of methylmyoglobin. So this methylmyoglobin is going to be the form of myoglobin that results from, just a second. Um, Here we go. Now I'm going to switch my share back. It's going to result from binding to an Fe3 plus cation. So this population of people in Kentucky, um, they had like a blue hue to their bodies because of the abundance of this methylmyoglobin. Now, by and large, they didn't really exhibit many other significant, what's the term, symptoms, but that was one thing that resulted. Now, if you do a Google search for blue people of Kentucky, chances are you're going to find this guy who's nicknamed Papa Smurf, and his skin has a very blue tone to it. And I believe that he is afflicted with this disease, not disease, but this disorder. Um, and you know what? I'm gonna go ahead and save us all the not the burden, but save us all the anticipation and the excitement. There is this fellow who I believe is a descendant of this population of people. Now, this is a, a unique population that they really didn't have access to roads in what we would kind of call our contemporary society for quite some time. But this is a symptom that's directly related to a disease that's directly related to a molecular explanation. I think that's always kind of interesting when you have something like there's an explanation, and that explanation is related to their heme or their hemoglobin proteins have a mutation that enable Fe3 plus to bind instead of Fe2 plus. Now, with that in mind, when you think about Fe3 plus versus Fe2 plus, or whenever I think about Fe3 plus versus Fe2 plus, the difference is one electron. In addition to that, that single electron causes that Fe2 plus ion to be a little bit smaller. Or sorry, that Fe3 plus ion to be a little bit smaller. So when we see this, when we were looking at the positioning of different atoms in that heme ring that would flux down, well, that Fe3 plus, it's not, if it's like this and then it binds oxygen and it goes like this, if Fe3 plus is present, chances are it probably starts out like this and then goes like this. So that results in a structural difference between your wild type hemoglobin and those afflicted with this methylmyoglobinemia. Okay, so in addition to that, wait, the guy isn't part of that. Wait, that guy isn't a part of the bluegrass thing. He drank colloidal silver. Oh, interesting. Well, sorry for my misrepresentation of that. I didn't intend to, and that was ignorant on my behalf. I apologize, everybody. So I will fact check myself a little bit better. Thank you, Andrew, for that, and Adam for support there. Um, so don't drink colloidal silver. And that is an instance where typically I'm not going to tell you what to do with your life. In fact, I pretty much never will. But in this case, I feel comfortable saying that. Okay. So in addition to oxygen being able to bind that Fe2 plus, carbon monoxide, NO, and H2S are all capable of binding to that Fe2 plus heme complex. Now, their binding affinity is higher than that of O2, which is one of the reasons that all these different gases are toxic. Now, what we're getting into today, the way that we're getting into this discussion of oxygen binding curves is ligand binding mathematical expressions. The dissociation of protein ligand complex can be written as an equilibrium. I don't know about you guys, but I remember whenever I took Gen Chem 2, walking away from it thinking, man, I feel like that entire class, or like 50% of that class was ratios and being able to write out a ratio based on an equilibrium. Well, we can use Or we can write protein expressions, protein ligand interactions as an expression. If we think about, as an equilibrium expression, if we think about PL as our product, our protein ligand complex, or P and L as our free protein and our free ligand. I got a private message, so does Fe3 plus prevent O2 from binding? I don't believe that it prevents it from binding. Instead, I think that the explanation is that there's a structural difference in after that O2 binds, how the protein has a different structure and different fate to it. Okay, so with respect to equilibrium expressions, we always want to think about our product and our reactants. We can write a protein ligand complex as a equilibrium expression as well. We're using PL as our product and free protein and free ligand as our reactants. So whenever we write this expression right here, effectively what we've got is our mechanism to write a dissociation constant, a KD, where we have our products and our reactants. So we've taken the protein ligand complex, PL, as one of the products, and simply written our expression backwards. Our protein ligand will dissociate into a free protein and a free ligand. Now, this is valuable because of the fact that now we've got a way to kind of relate concentrations of different things to basically affinity. Because if you think about a KD, you have a measure of affinity. How much does this thing want to bind this other thing? Now, with that, in most conditions, in most circumstances, the ligand concentration is extremely large compared to the protein concentration. Therefore, that PL complex does not appreciably change the ligand concentration. Now, what we are interested in, and this is going to be kind of our foundation, is we're very interested in the fractional percent of ligand binding sites that are occupied and how that can be represented. So we use theta. Theta is set equal to a ratio of the number of binding sites that are occupied, okay, and the total number of binding sites in a solution. So if you think about that in terms of our expressions as PL and P and L, PL, PL, well, let me ask you this. Does PL have an occupied binding site? It does. Now, does P have an occupied binding site? No, it does not. Because that protein has a binding site for the ligand, but it hasn't bound to it. Now, our free ligand, on the other hand, well, that doesn't have a binding site because we're talking about this kind of in a protein-centric world, you could say. So what we've got here is an expression where theta is equal to number of binding sites occupied divided by the total number of binding sites in solution. So we've got PL, or concentration of PL, to represent the total number of binding sites that are occupied. Number of binding sites that are occupied, and then free P, free protein, plus the concentration of protein ligand. Because on the bottom there, that's going to represent the total number of binding sites. Some of those binding sites are left vacant. Some of them are occupied. Oh, damn it. Sorry for swearing. There we go. Okay. So what we can do with this is we can manipulate this equation. We can take the expression that we got previously, our KD, and take this theta and say, all right, well, effectively, we know that PL can be rearranged, or this KD expression can be rearranged. We could do the algebra to rearrange this right here. This right here. How do we do that? Well, one thing that we're going to do is we can multiply each side by the concentration of PL. So that's going to give us PL. Okay, so now we've got PL, concentration, times KD equals PL. Okay, divide each side by KD. Okay, every time I say KD, I do think of basketball superstar Kevin Durant. We're going to divide this by Kevin Durant, protein concentration, ligand concentration divided by KD. Now, the great thing about this is now we have an expression that we can use to substitute for this right here, our theta, or we can plug into theta. And when we do that, what we're going to get, this dissociation equilibrium equation can be rewritten as, booyah, PL, what I just wrote. The great thing about that is now we can substitute that into two different places in our theta expression. Boom, boom. That allows us to take that theta expression and put it in terms of PL and KD. Now, with that said, I like saying that phrase. What is theta if you have 60 free proteins and 65 protein ligand complexes? What is theta? We're not dealing with concentrations. So in the event that you're thinking, I can't solve this, there's no concentrations, just use the numbers that are provided and imagine that they're concentrations. We're just doing this kind of as a conceptual approach. We've got 36 seconds. This is not a question where everything's on the table. This is, let's get our feet wet with this one. 20 seconds. I'm gonna put another 15 on the screen. We got 30 seconds left because I want to get some good answers. Wide range of answers. Oh yeah. Oh yeah. Ten seconds. And scene. 0.52 is correct. 0.52 is correct because what we wanted to do here, this free proteins is effectively P. This is PL. We had theta, which is what we're looking for, which kind of looks like if you've ever watched South Park, Terrence and Phillip. This is our PL, so 65 divided by our total number of binding sites. So that would be P plus PL, so that would be 125. So we're looking at 0.52. Or another way that you could put it is 52%. So 52% of the binding sites are occupied in this scenario that I've provided. Now, if you got 1.83, which 13 folks did, that just means that you did your equation incorrectly. If you got 65 or 125, no, those are no. And then cannot be determined. That's also incorrect. Okay. The 65 and 125, those are put in as decoys, as just like, hey, here's a number from the equation, from the question. Let's see if you'll use this. So ligand binding math is great. And math is powerful. It's great. Helps you make money and helps you land rocket ships on the moon or other places. We're going to substitute all these expressions and give us a simplistic version of theta. Theta is equal to our ligand concentration, and it's not bracketed there, but I'm going to go ahead and draw that bracket in because we're still talking about concentrations. Now, the reason that it's not bracketed here is because we're talking about a unique protein. And that unique protein or unique proteins that we're talking about are hemoglobin and myoglobin. Sure, they're just our models, but that bracket indicates molar concentration. And when we talk about a protein that binds a gas, we kind of got to make a little bit of a modification to how we discuss this. So there's our simplistic rendering. theta is equal to ligand concentration or amount of ligand over our KD over or plus our ligand concentration. Now, this equation allows us to express the fractional percent ligand binding sites occupied as a function of our ligand concentration. That's beneficial because that's something that we can have a better control of. Like if we want to determine the binding affinity of something, we know how much of our ligand that we add. Protein is a little bit more difficult to calculate. So this is very helpful. Oh, forward. Now, visually, the expression or this equation represents a hyperbolic curve. Okay, so there's our first point where we're talking about taking this equation and putting it into a curve form. But before we do that, let's go back to our example. Our example is myoglobin or hemoglobin. We're going to start out with myoglobin because it's a little bit simpler. Now, as it is a little bit simpler, or the reason that it's a little bit simpler is because myoglobin binds to one O2 molecule compared to four, where it's a little bit more complicated. Now, how does the binding of O2 to myoglobin vary with oxygen pressure? Okay, so O2 is a ligand to myoglobin. We're not investigating or curious about heme because when we are thinking about a wild type myoglobin or hemoglobin, we can go ahead and operate under the idea that that heme molecule is present. So only if you have a mutant myoglobin or hemoglobin are you then going to say, oh, well, what about um, the iron binding, or is heme even bound? For this, we're defaulting to a wild type and um, yeah, a wild type form of hemoglobin and myoglobin. Damn. Sorry for swearing again. So in this case, our protein ligand complex is MbO2, and that shows our perfect ratio of one myoglobin and one O2 molecule, MbO2. That's our complex. Our protein, our free protein is Mb, and our free ligand is O2. So what we can do is apply this to our Kd expression, where we've got Mb and O2, the concentrations of those, over. You're right. You're right. I should do that. Mb is our wild or our free protein. O2 is our free ligand. MbO2 is our complex. So we can rearrange that. Now here's where something got introduced. And this is an important thing to include. I'm going to use the arrow. Oh, I'm going to use the star. Boom, 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 boom. Lowercase p. What does that lowercase p mean? Oof. That usually indicates partial pressure. Perfect. Now, when we talk about gases and multiple gases, if you remember, I think it was Gen Chem 1, you talk about gas ratios and your mole fraction, your gas fraction, mole fraction. Um, Here, what we've got is P sub O2 or PO2, I'm sorry. Now, the important thing about that is we can use, and since it's nearly Halloween, so I'll, I'll, I'll say this instead. We can use Chucky's law or Charles's law. I don't mean disrespect, but in the season, Charles's law says that a quantity of gas absorbed by a liquid is proportional to the partial pressure of the gas above that liquid. So you can use a system where you can measure the gas concentration, or you can determine the gas concentration above a solution and then presume that, well, this gas is going to be absorbed in that liquid. That liquid being the solution with our myoglobin protein. So now, with that in mind, thinking about gases, we have a concentration of an O2 um, is a corollary to our partial pressure of O2. Now, with that in mind, we got a question with some wonderful little stars. Which of the following would be accepted units for measuring the partial pressure of a gas? Oof. Hmm. Hmm. This one's kind of tricky. We're getting some good responses on this one. I'm happy about that. I'm not looking at the responses, I'm just saying the numbers. We're trending towards getting 45 plus. We got 12 out. Okay, we're getting there. Yeah, I think we're going to get 45 at least. We might crack 50. 49. We did it. We did 50. Good. 55. That's a good number. 55 out of 57. That's pretty good clearance rate. Now, with that in mind, let's check out the correct answer. 46. Great job, everybody. You did better on this one than I think our last question in terms of our number of answer options. I'm happy that no one said pounds because we know that's not a concentration. The correct answer when we're talking about the partial pressure of a gas, there's a number of different ones, but what I want you to be most comfortable with is torr or torricelli. That's the same as millimeters mercury. 1 torr is equal to 1 millimeter mercury. You could also measure partial pressures of gas using kilopascals or bars or something like that, but we're going to use torr, and so that's what you should be accustomed to seeing. Now, what can we learn from our KD with respect to this expression over here? Okay, so KD is equal to our concentration of myoglobin times our partial pressure of our O2 divided by the concentration of our complex. We use KD to express the affinity that a protein has for a ligand, and in this case, oxygen. So the lower the KD, the higher the affinity. So KD and affinity are inversely related to one another. Now, that's an important point to keep in mind, to remember, because whenever you see a low KD, that indicates that that molecule is very tightly bound and it has a very high affinity for it. Now, when it comes to our oxygen binding math, that theta expression, think about theta as being most relevant for protein ligand complexes. When it comes to oxygen binding proteins and those protein ligand complexes, we just substitute theta for Y. So effectively, Y and theta are more or less the same. The expression is the same there. We've got our concentration of our complex divided by the concentration of our complex plus the free protein. Now, the fractional percent of O2 binding is also known as the percent oxygen saturation. Now, I don't know if anyone has a smartwatch. I've got a Garmin Forerunner 945. If you have an Apple Watch or any other watch like that with more than likely a sensor like mine, there you go. It's blipping or it's lighting up. What that is doing is it's getting a good sense of my blood O2 saturation. So that's measuring the amount of light that's absorbed by my blood in the visible light spectrum and in the infrared spectrum so that it can give me a sense of, oh, well, your blood is 95% saturated with oxygen. The higher that number is, the better. But that's always kind of a number from a clinical standpoint. My understanding is that when it gets to like 90 or below, that's a pretty bad state. Chances are you're going to have supplemental oxygen. Okay, so the fractional percent of O2, known as our percent oxygen saturation, that is Y. Now, here is where we're getting to graphing it. We can take that Y expression and we can take these two expressions and rearrange them, just like we did with the PL expression. But here what we have is Y is equal to PO2. So I will use this term, I'll use these two terms interchangeably, the partial pressure of oxygen and the concentration of oxygen. The only thing that I need you to remember is that whenever we talk about the concentration of oxygen, that is going to be measured in torr. So what we have here is our partial pressure of O2 divided by our KD or our affinity for O2 plus our partial pressure of O2. Now that equation right there is displayed with this graph right here. This is an example of an oxygen binding curve. What is the fractional percent or fractional percent of oxygen at a specific concentration of O2. So when we look at one of these graphs, that's the question that we're looking to answer. And the way that we do that is we look along the x-axis. So for example, we want to find the coordinates. Let's say you have a myoglobin protein that is in an environment where the O2 concentration is 15 torr. My question for you is what percent of that myoglobin protein is saturated with oxygen? So we look along our x-axis and then we find the coordinate. So if you were to make an estimation based on this picture right here, what percent of myoglobin do you think is saturated? You got about 80%. I like that. Boom, right there. We're going to line that up and boom, a little bit more than 80%. I like it. Great job, Andrew. So that's what we're looking to do. We want to find out what O2 concentration gets our protein saturated and what percent saturated. So that gives us a measure of our protein's binding affinity for O2. Now, with that said, along that x-axis, if you move to the right or move to the left, you're increasing the O2 concentration or the partial pressure of O2, and therefore that myoglobin protein is becoming more saturated or less saturated. Now, when O2 binds the myoglobin, the binding increase is hyperbolic with the pressure increase. There are 2 points on this binding curve that are very important. One of them is what is known as our half saturation point. So in that case, what we're going to do is we're going to look along our y-axis because whenever our y-axis reads 1.0, effectively our protein is 100% saturated. What our y-axis or the point on our y-axis where we find 50% or 0.5, so that would be 0.5 or 50%. That is the concentration that gets our protein to half saturation. Now, one thing that I want you to notice about this right here, our protein's never going to become fully saturated because one thing to keep in mind is we're talking about a population. We're not talking about just one myoglobin protein because one myoglobin protein will become saturated very easily. It binds 102, done, saturated. We're talking about a pool of, say, 100,000 copies of myoglobin. Is every single one of them going to be saturated at the same time? No, it's not. Because the point is they're going to bind O2 and release O2 as they need, or as the cell demands. So we have what is known as an affinity constant, which is really the number that we're most interested in. That it's known as a P50. That is where our KD is equal to PO2. That is then where our fractional percent saturation, or Y, is equal to 1/2 effectively. Now, when our PO2 is equal to our KD, then 50% of the ligand binding sites are occupied. Our KD is often called a P50. Now, this P50, and what I want you to know about P50 is this is a measure that lowercase p indicates that we're talking about the partial pressure. So that P50 is a kind of unique number for oxygen binding proteins. So we've talked about, and we'll use different terms based on different types of proteins, but a P50 is basically an oxygen binding protein's affinity for its substrate or for its ligand. Now, oxygen pressure, so it is the oxygen pressure where myoglobin is 50% saturated with O2. A high P50 means a low affinity, and a low P50 means a high affinity. So it's got that same kind of inverse relationship that KD does. The higher a KD, the lower the affinity. So the way that I think is helpful to think about that and the way that you can process that information is think about it as like needs based. This protein needs how much O2 to be half saturated? Well, If it needs more, then its affinity is lower. So with that in mind, I want you to think about this. What are the units for P50? What do you think the units are for P50? Let's see, last time we got 50 responses. I think we can do that again. Let's do that. We got 33 seconds left. We're going to do 50. Yeah, we got 49. I think we got 55 out of 57 last time. We're not going to do that. Oh, we're going to 56 out of 57. Good job, everybody. That's what I get for being a negative Nelly. Tor is correct. So P50, I'm happy that you answered Tor because P50 is the concentration or the partial pressure of O2 that gets your protein to be half saturated. And that's an important thing to know whenever it comes to binding affinity, that this has a unit. I think that there's a tendency for people to think about, oh, well, that's a constant, or that's something that doesn't have a unit. But this does, absolutely. Okay, so O2 binding parameters are y-axis. When we're talking about an oxygen binding protein, we really want to represent it as y as opposed to theta. Am I going to dock points or have a question that's asking, is this y or theta? No, I'm not. But this graph is showing, well, this is using the model, but also kind of applying specifics. So our y-axis is labeled y for the fractional O2 binding affinity, or fractional O2 bound. Our x-axis is partial pressure of O2. So that is our partial pressure of oxygen. Here's a simple binding curve for representing myoglobin. A nice hyperbolic curve. It goes up and then it kind of plateaus. Done. Do we ever reach 100% saturation? Nope. It's just not realistic for what's going to happen. Now here's another curve. Just imagine that this is a different myoglobin mutant. What do you notice about this one? Well, one, it doesn't go up as dramatically. Instead, it kind of goes up and plateaus much earlier. So what do you think the P50 is for each of these proteins? Well, we've got our wild type, which I'm going to label with the red, 50% saturation. Boom. Okay, so this is I'm going to call that 10 Tor. Okay, now our other protein, let's call that 40 Tor. Go ahead and add to the chat. Which protein do you think has a higher affinity for oxygen, X or Y? Higher affinity. We got one vote for X, 2, X question mark. Now, our P50 is the O2. You got to vote for Y. Is the P2 or PO2 that gets our protein to 50% saturation. Okay, so there, what we're doing is when we want to determine the P50, we look at the y-axis and basically say, okay, there's the top, here's midpoint, 50%. What is the concentration or what is the partial pressure of O2 that gets these two proteins to 50% saturation? Well, protein X had a PO2. I like that explanation there. Milo says it's X because it gets the 50% oxygen faster. I would make a minor tweak because then you're talking about rates and it would just be with a lower concentration. We're not really expressing anything about rates. But I like your thought process there. X only needs 10 torr, whereas Y needs 40 torr. So the P50 for X is lower, which means I'm going to say BA binding affinity is higher. Okay, it's 9:50. There's a little bit more content on this slide. We're going to kick that off on Friday. Um, I hope that you guys have a great day. I will see you guys Friday morning. I'm going to end my share. I'm going to stop my share. And yeah, enjoy your day. I'll see you. Yeah, I'm going to get them up on Friday. Absolutely. You guys have a great day.